So, hello everyone. My name is Charishma, Solution Engineer in Low Frequency Electromechanical GTT. I'm going to demonstrate the demagnetization effect on the permanent magnet machines. So, I believe many of us already know this demagnetization phenomena. But let's just start with a quick introduction. So the loss of permanent magnets' magnetic properties due to the temperature or strong external magnetic fields that is leading to the reduction of machine's performance is typically known as demagnetization. As you can see that for the typical demagnetization characteristics, we enter into the second quadrant of the BH curve. So you can see from the curve, we have a load line. So if our point, a working point is above the load line, say for example, K as shown in the picture, so this will be a normal operation and the machine continue to operate in the KB line. If we have the working point below the load line, say for example T, then what happens is the magnet will partially demagnetize and follow the recoil curve. So that is called, which is shown in the dotted line, dB dash. So this is typically represented in the second quadrant for an hard magnetic materials or the permanent magnetic materials. So in the next slide, we'll be seeing the effect of demagnetization with respect to the temperatures in two examples. So N32 magnet and N45 magnet. As you can see on the screen, as the temperature increases, the knee point is is shifted higher. So this is one of the effect of the temperature in second quadrant and can be represented using the demagnetization curves. So next, currently we have seen the short circuit analysis by my colleague. So you can see that short circuits also can lead to the demagnetization. So I'm going to explain you how it happens. So in the short circuit, that are typically the stator winding faults or inverter faults, we can see a severe current surges. So these current surges will create a strong magnetic fields, and indeed these strong magnetic fields will act against the magnetic fields of rotor magnets, thus resulting the demagnetization, or it can also cause a thermal stress. So the short circuits usually generate excessive heat, which may rise the rotor temperature beyond the magnet thermal result. And we have just seen that effect of temperature on the demagnetization curves. So yeah, this is how the demagnetization happens due to the short circuits. There are two main reasons are the strong opposing magnetic fields and the thermal stress. So we can see the workflow in the SimLab and how do we perform the demagnetization effect and how do we represent the model we can see now. So I'll just start with the model my colleague showed. So you can use the same model for the demagnetization effect also. The procedure will remain same even in the case of the working point analysis, or if you're looking at cogging torque, or if you're looking at the back EMF, the procedure will remain same. Only the difference is that you need to make sure that the magnetic property is set to the nonlinear magnet as shown in the screenshot. So to do this, you can enter into the material dialog box from the menu analysis, and you can just use the material and then create it. So if you have an existing material, you can just edit it by double tapping on it. So the both will be the same. So you can see that I have selected a category of solid and the class metal, and everything will remain same for the short circuit analysis as well. So only the change I am making is converting the BH curve from the linear to nonlinear characteristics and then entering the nonlinear characteristics properties like the corrosive field strength, the maximum relative permeability, and transversal relative permeability. Once if you change the magnetic properties, then next is that you need to select the demagnetization option in the load and constraints of the magnets. For that, you can just, if you have already the model, you can just click on double tap to edit it, and you can just check the demagnetization option here as shown in the window. Or if you're starting from the beginning or creating the magnet, you can just uncheck at the beginning itself. So the procedure, make sure that you select the demagnetization. In here, I just want to bring a note, important note here. If you are not selecting nonlinear magnetic properties in the material, the SimLab is going to show you a warning, letting you know that you are using linear permanent magnet material and you can't check the demagnetization option. So make sure that you just use a nonlinear magnet for the demagnetization. Otherwise, it is going to give you a warning. So this way you can check whether you're using a good nonlinear magnet for your simulation. So now once if you adjust a nonlinear magnet and then adjust the demagnetize and then check the demagnetization option inside the magnet load and constraints, now you are ready to solve the model. You can just click on results and then update the results as demonstrated earlier. So once the results um, uh, once the model is solved and the results are ready to see, you can see that you can just see the B, the magnetic flux density initially, but in order to see the representation of the demagnetization, you need to switch from the B to the BR magnet. For that, you need to enter into the component, and you can see a little down arrow there. If you click on that, you can see an options here. There you can select the BR magnet. Once if you select the BR magnet, and then it is going to display you the magnetic field density on the magnet as seen in this picture. So you can see the areas where the demagnetization happened. It is presented in the contour format. If you're not if you're interested to see in the arrows format, what you need to do is you need to switch the plot from the contour to the vector, so you can see both in the arrows and in the ISO values as well. So I'll just take this chance to directly show you in the SimLab model. So you are seeing a completely solved model here. So where I have represented already, I have selected the component BR from this component option. And then I have used the contour option here. So you can see the areas of the demagnetization here. You can see the color difference between the red part and slightly orange part. So this indicates the demagnetization happened and it is considered during the solving. So you can also just switch between the contour and vector to see the areas of the magnet. You can see the little orange areas where the magnet is demagnetized, and if you want to calculate, if you want to see further calculations of the demagnetization, you can just go into the Flux browser and can do further post-processing. Yeah. So this is a short and quick introduction of the demagnetization in using this Altair tool SimLab. So thank you.